Hello. Today I would like to talk about data preparation for reliability analysis. Before attempting reliability analysis, we need to be sure that our data adheres to certain rules. The rules are simple, but data preparation prior to reliability analysis can be laborious as well as futile when the data does not follow the rules. The Mesh Living Reliability-Centered Maintenance process ensures that work order data is of analytical quality. Living RCM ensures 1. That failure modes are precisely identified on the work order. 2. The failure mode's life-ending events are correctly recorded. And 3. That the RCM knowledge base remains consistent with reality and with the EAM's catalogs. When our work order process respects these three criteria, clean data samples for analysis will be generated automatically by Mesh. Otherwise, we will have to prepare the data sample prior to attempting reliability analysis. Sometimes this preparation step is referred to as data cleaning. In this video, I'll demonstrate the cleaning procedure. Here is a set of data provided by Hyro, a reliability engineer responsible for a shovel fleet. The data consists of two Excel files, Eventos, or events, containing the work order data, and Inspecciones, containing the condition monitoring data. Data problems are almost always related to the events table, so that's where we'll focus our attention. Notice that the events table has 552 records or rows. The columns identify the shovel unit, the date of the maintenance event, the unit's working age at the moment of the event, and column 4 contains the events themselves. I sorted the columns by ident and then by date. Logically, a unit's working age should increase as the date increases. Indeed, reliability analysis requires that our data sample respect this logical requirement. When this rule is violated, the data will be unsuitable for Weibull or any other kind of reliability analysis. The data, by definition, will be dirty. It is important to note that one may still go through the mechanics of reliability analysis on dirty data, but the results will be of limited value. They will not support our objective, which is to achieve actual reliability from data. Turning our attention to the events column, B symbolizes a life-beginning event. The shovel's hour meter reads 0. OC is an oil change event. The reliability engineer, Hyro, decided to include oil change events in the sample because he believes that they may be relevant to prediction. In previous videos, we learned that an oil change is a type of non-rejuvenating event. It affects the condition data, but not the asset's condition. Scrolling down, we notice that the event symbol EF1 says that failure mode 1 occurred and was renewed on April 22, 2011, when the shovel's hour meter read 13,664.93 hours. The subsequent B event, having no appended numeral, is taken to mean that there was a complete overhaul and all unfailed failure modes were restored to as good as new condition, not just failure mode 1. If we look at the filter list, we see 5 possible failure mode ending event types represented in the data, but only one B or beginning event without an associated numeral. We infer, confirmed by Hyro, that when any of the 5 failure modes occurs, it is maintenance department practice to renew all 5 failure modes, 1, 2, 3, 4, and 6. By the way, we don't have to number the failure modes. We can use up to 20 characters of text to symbolize these events in the data. If a blanket renewal were not the policy, then the symbol B1 rather than B would have been used to symbolize the renewal of only failure mode 1. The other 4 failure modes would continue to accumulate their individual usage hours from the point that the unit is brought back into service. They would not be zero-timed by the modeling software. The events table constitutes our age data sample. We intend to perform reliability analysis upon this data in order to develop a failure prediction model. If you are thinking that the events table is important, that we need to get the events right, you would be correct. In fact, inadequate event data is the primary obstacle to predictive analysis in maintenance. The living RCM process described in previous videos addresses the challenge of achieving analyzable events data. Open Exact for modeling. The first thing we'll do is create a new working model database. We'll call it shovels_WMOD. Delete the default tables. They are pre-structured for a simple asset having a single failure mode. Our shovel can be subject to multiple failure modes. For this reason, it is referred to as a complex item. Set up the project data. We'll call it shovels. In the CBM model box, we'll use the word shovel as the base model name to which we'll append the names or numbers of the individual failure mode models that we want to create. Hit Modeling, Data Setup, and enter the attached script. The script attaches the WMOD database to the relevant tables in shovels_MES, whose events table we examined previously. Hit the Marginal Analysis button. Marginal analysis refers to complex items. A dialog pops up. I'll specify the first failure mode for which we want to build a predictive model. Change the extension to 1. Any descriptive text can be used here. I have no idea what failure mode this is, so I'll just number it as its events are numbered in the events table. Next, we'll tell the software which equipment units in the data sample to include in the analysis. The software has created this list from the equipment unit identification column in the events table. We'll select all the equipment units in the shovel fleet. Next, we'll map the event symbols of all failure modes recorded in the events table to events that regard failure mode 1. We'll assume, as already mentioned, that the organization's maintenance practice is to renew all failure modes when any one failure mode fails. Begin with the B event. The software has found this symbol in the events table. It did not find a B1 or B2 or any failure mode specific beginning event. So we'll map B in the data to B in the model for failure mode 1. We'll give it a high precedence since a beginning event will always occur later than any other event, such as a failure or suspension that may occur on the same date. B then indicates a complete renewal of all failure modes. The EF, or ending by failure event, will map to itself. We'll assign EF a relatively high precedence of 8, since it would be one of the later events to occur on any given date. Any EF1 symbol found in the events table will map to an EF event in the model for failure mode 1. All other failure modes that occur in the data, according to understood practice, would result in the suspension of failure mode 1. We'll give the ES, or ending by suspension event, a precedence of 9. By convention, we assign it a higher precedence than that of failure, although it is impossible that both could occur at the same date and time. Similarly, for failure modes 3, 4, and 6. ES and OC events will map to themselves. We'll give each OC a precedence of 1 to ensure that it will be considered by the algorithm to have occurred later than a NOIL analysis inspection, should they happen to occur on the same date. The inspection's precedence is defined internally as 0. We have just mapped the occurrences of failure modes 2, 3, 4, and 6 to the preventive renewal, in other words, the suspension of failure mode 1. Finally, we'll map the names of our condition monitoring variables to the names that we would like them to have in the proportional hazard model equation. The data mapping for failure mode 1 is complete. Since there are 4 additional failure modes, hit the More Models button. Select Model 1 as the basis for the next model. The failure mode's name is automatically incremented to 2. If failure mode 1 occurs, what happens to failure mode 2? According to our assumption, it will be suspended. Of course, EF2 in the data should map to EF in the model for failure mode 2. EF3, 4, and 6 will remain unchanged. Hit More Models again. In a similar way, we'll map what happens to failure mode 3 if other failure modes occur. EF2 now maps to a suspension. EF3 to a failure. Hit More Models. Now map failure mode 4. There is no failure mode 5. Once failure mode 6 has been mapped, hit OK. I'll point out here that had the principles of Living RCM guided work order data entry mapping of failures of one failure mode to suspensions of others would not have been necessary. Mesh LRCM ensures that all failure and suspension events will have been correctly identified at the source, that is, at work order data entry by the technician. Now for the main purpose of this video. We will perform a sanity or integrity check on the data prior to running the algorithm that will construct the hazard model. The investigation begins with the data surrounding failure mode 1. Under the Edit menu, hit Check Database and select Data. A general report on the data governing failure mode 1 appears. It says that there are 12 units in the sample, 43 life histories, of which 12 were failures, and 24 were suspension events. We recall that there were no individual suspensions identified in the data. Therefore, all of these suspensions were a matter of the policy that we spoke of. They will have been created by the mapping procedure consistent with that policy. The report tells us to check two tables. Those tables will list potential data issues that the data function has revealed. Hit the Data Check table and arrange it at the top of the screen. Click the Description heading. Two things will happen. The description opens up for readability, and the table records order themselves in chronological sequence. Each data check record warns us of a possible problem in the data. We'll investigate each warning in the data check table. Open the CMI inspections table and arrange it below the data check table. When you select a row in data check, the CMI inspections table will scroll to the record referred to in that warning. The hazard modeling algorithm that we will invoke once the data is clean will parse each record in CMI inspections. Working row by row, it will build up the probabilistic relationship between condition data and any failure events that may be associated with specific condition data patterns. For the process to be sound, the date and working age sequences must both increase monotonically regarding a given unit. Whenever a unit's working age decreases with calendar time, this will violate the basic rule we spoke about earlier. So any lack of coordination between calendar date and working age indicates an error that should be corrected if the algorithm's result is to be relied upon. In other words, if the data is dirty, to use the vernacular, confidence in the predictive model will be reduced. Dirty data is a chronic problem in maintenance databases generally. To achieve reliability from data, the maintenance organization should enforce sound living RCM practices. Engage synchronization between the two tables by clicking on the second, then on the first record in the data check table. The first warning asks us to check whether the unit at the date specified is currently in progress. If it is, there is nothing we need to do. In fact, we can see that it is indeed a temporary suspension because it is the last record of the unit 611-134. The next record is a different unit. We can say this unequivocally because the table has been sorted by unit and then by date. The software has correctly created a temporary suspension record distinguished by the symbol *ES. The next 7 records are similar, and I have confirmed by the same reasoning that their units are currently operating and that the software has correctly inserted a temporary ending by suspension event. The 9th record, however, is different. It says that a history beginning on April 12, 2017 has no condition monitoring inspection data. Since today is only April 18th, this is quite probably correct. The unit was brought into service only a few days ago. We deal with this data by deleting the entire 4th history for unit 611-135 that began and ended on the same day. Since it no longer appears in CMI inspections, this history will not be parsed by the proportional hazard modeling algorithm. The next warning says that the referenced record has a larger working age than the subsequent record. Of course, such a situation violates our basic rule. Sure enough, the working age, 1220.72 hours at oil analysis, is larger than the OC event, which occurred subsequently in time. Obviously, this is a rounding error. I'll change it to 1221. Proceeding to the next record, we have a similar problem. where the hours on the oil change event are lower by 1 hour than the preceding inspection. We'll fix this in a similar manner. The next warning takes us to Unit 611-381 on January 30th, where we see that 2 oil analysis samples were carried out at the same working age. This is easily fixed by eliminating one of the records. Now that we have a clean set of data regarding failure mode 1, we may proceed with the analysis. Hit the modeling button followed by the Weibull PHM button. We select our candidate variables for this model. Normally, the reliability engineer has some ideas based on theory and practice on which monitored variables are likely candidates for prediction. I, however, have no information on what this failure mode actually is. It is referred to only as failure mode 1 in the events table. So I'll take a guess and try iron, a common condition assessment variable. But we see in the hazard modeling report that the PHM algorithm has found no influence of iron on failure probability. It has, however, found that age may be significant by indicating Y for yes, but age is a stand-in for other variables that are either unmonitored or not yet considered in the model. Since iron, a wear metal, is not significant, let's try a monitored variable related to oil condition, say oxidation. We see that oxidation, in addition to age, is found by the PHM algorithm to be a significant risk factor. There are a few statistical tests that we can use to assess this proposed age and oxidation-based model. One such test is a graphical evaluation of the residuals from the estimation. If the residuals corresponding to the failure events, represented by the red squares, are distributed around the normal at 63%, the model could be considered a viable one. We can get a visual idea of the relationship between oil oxidation and the occurrence of failure mode 1 by viewing the 2 sets of data simultaneously. Hit View and Inspections. Uncheck the Select All box. Deselect all the elements but Oxy. Check the Include Events box and hit OK. We have a failure event that occurred here, but no significant oxidation preceded it. This failure then is possibly unrelated to the level of oxidation in the oil. Let's proceed to the next unit. A failure at 25,000 hours was preceded by notable levels of oxidation, thus supporting the PHM algorithm's findings. Similarly, a sharp rise in oxidation preceded failure mode 1 on unit 611-135, and on 136, and so on. We may surmise that oxidation could be a useful predictor of failure mode 1. How good a predictor will be determined in subsequent steps of our analysis. Close the Inspections view. We'll name this model Oxy by selecting it again and rerunning the PHM procedure. Now that we have a probability relationship between an oil analysis variable and actual failure of failure mode 1, we'll need to incorporate the notion of prediction. To accomplish that, we'll represent the patterns of change in the variable of interest, oxidation. The method is based on the Markov failure time model. Hit the transition probability model button. Now hit transition rates. All probabilities of moving from any variable state to any other state as a function of time. The software has, having examined all past changes, proposed reasonable divisions in which to classify monitored variable levels. In this case, there is just one monitored variable, oxy. Hit OK to accept the proposed classification. Hit the Display Survival button. We may illustrate the predictive concept by selecting some working age within the lifetime of a unit, say 8,000 hours. We'll also specify a practical observation interval, say 250 hours, for making data-based decisions in maintenance. What would the probability pattern describing changes in the state of oxidation look like? The pattern is represented in a transition probability matrix. According to historical changes, if oxidation is currently in state 2 at 8,000 hours, its probability of remaining in that state at 8,250 hours will be 53%. If, on the other hand, it is currently in state 4, the probability of failure in 250 hours is 4%. In this manner, we have introduced a predictive element into the decision model that we are in the process of developing. The final element in prediction incorporates business information in order to establish a risk model. Hit the Decision Model button. Hit the Decision Model Parameters button. Here we'll enter the business information for evaluating risk. We assume a 10-to-1 ratio between the relative cost of failure and the cost of preventing or mitigating that failure's consequences. Enter the observation interval, a currency unit, and hit OK. A classical cost model that you have probably seen in textbooks is displayed as a graph. The vertical axis measures the combined cost of repair and failure of failure mode 1 in a unit of time. The horizontal axis measures the amount of risk a maintenance organization may wish to assume with regard to failure mode 1. We note a low point on the cost curve. The corresponding value on the risk axis reports the optimal level of risk. It is the risk level that will result in minimal expenditures related to that failure mode. In a few minutes, we'll learn the precise decision rule we should apply to our condition monitoring data in order to attain this optimal risk so as to achieve minimum cost as a maintenance decision policy. But before we do that, let's examine the cost model in more detail. The software will tell us just how much money implementing the optimal CBM decision model will save. Hit the full report icon. If we adhere to the optimal CBM policy, we will save 74% over an ineffective CBM decision policy or a run-to-failure policy. This assumes the 10-to-1 cost ratio that we built into our business model. In another video, we illustrated a method for validating cost ratio assumptions. We've seen the cost model, but we don't know yet how to interpret our condition monitoring data so as to achieve the optimal CBM decision policy. What does that optimal decision model look like? Close the report and hit the Optimal Policy button. This graph should govern our decision process if we wish to optimize the way we interpret our CBM data. If we adhere to the graph's recommendations, we will attain the lowest cost with regard to the failure mode in question. The vertical axis represents our monitored data. The horizontal axis is the unit's working age. If our monitored data falls in the green area, the optimal decision is to defer action until the next observation. If in the yellow area, the software will provide time estimates for optimal intervention. If in the red area, we are already in a potential failure state and immediate intervention is recommended. Let's run the optimal decision policy against our current data. Hit Decisions. Select some units. Check Report Conditional Density. The optimal decision policy graph appears. The condition data observations are points on the graph. The optimal policy graph says to continue operating Unit 611-133 normally. Hit Page Down. The failure probability graph appears. Unlike the first graph, it does not account for business data. Instead, it is based purely on probability and prediction. It says there is only a 0.1% chance of failure in the next 250 hours. Hit Page Down again. This is the conditional distribution function. It is the converse of the survival function. Hitting Page Down one more time brings up the conditional probability density graph. Hitting the full report icon shows us the estimated remaining useful life regarding failure mode 1. We are currently at 2,132 hours. The graph reports that we have a remaining useful life of 7,128 hours with a confidence measured by the standard deviation of 2,565 hours. Other ways of expressing confidence in the CBM decision are shown in the table. For example, there is a 50% chance of failure between 7,500 and 11,000 hours. Let's summarize what we have accomplished over the course of this video. First, we examined the data and removed errors that could compromise our analysis. Then we performed the hazard, transition, and business analyses. And lastly, we assessed the benefits of applying an optimal CBM policy for failure mode 1. In previous videos, I showed how to implement multiple CBM policies conveniently in an automated intelligent agent operating silently on the corporate network or in the mesh cloud. The final thought I will leave you with is that reliability analysis precedes reliability improvement. But reliability analysis requires clean work order data, which can best be achieved by incorporating living RCM into the work order process. Thank you.